The discovery made by the MeerKAT Radio Telescope in South Africa marks an extraordinary step in our understanding of interstellar visitors to our solar system. Following the detections of 1I/Oumuamua in 2017 and 2I/Borisov in 2019, 3I/Atlas became the third known interstellar object to pass through our solar system. Its recent observation by MeerKAT represents not only the first radio detection of 3I/Atlas, but also a crucial confirmation of hydroxyl OH molecules associated with its surface or surrounding coma. This detection provides deep insight into the composition, motion, and physical conditions of material ejected from this interstellar traveler. MeerKAT, operated by the South African Radio Astronomy Observatory, SARAO, is one of the world's most sensitive radio interferometers. Comprising 64 dishes, each 5 meters in diameter, MeerKAT functions as a powerful instrument capable of detecting weak cosmic signals at frequencies ranging from 580 MHz to 14.5 GHz. Designed originally as a precursor to the Square Kilometer Array (SK), MeerKAT's combination of high sensitivity and wide field of view makes it ideal for studying faint emissions and absorptions in the radio regime, including those arising from interstellar molecules. During its October 24, 2025 observation session, MeerKAT turned its focus toward 3I/Atlas. At that time, the interstellar object was located merely 376 degrees away from the Sun, about 7 times the Sun's apparent diameter in the sky. Observing such a target so close to the Sun is extremely challenging due to the intense solar background noise that can interfere with radio measurements. Despite these difficulties, MeerKAT succeeded in capturing a clear radio absorption signature attributed to hydroxyl radicals, OH molecules. The detection reported by DJ Pisano and collaborators in the Astronomer's Telegram focused on 2 specific spectral lines corresponding to hydroxyl OH transitions at 1.665 and 1.667 GHz. These are well-known frequencies in radio astronomy, often associated with the presence of water dissociation products in comets and molecular clouds. The presence of OH indicates that 3I/Atlas likely contains water ice or hydrated compounds that were released and subsequently photodissociated by solar radiation. The 2 detected absorption lines corresponded to Doppler velocity shifts of -15, 59 plus or -0, 16 kilometers per second and -15, 65 plus or -0, 17 kilometers per second, respectively. These shifts reflect the relative motion of the absorbing gas along the line of sight. Moreover, the full width at half maximum FWHM of the lines was measured to be 0, 88 plus or -0, 37 kilometers per second and 1.26 plus or -0, 40 kilometers per second, indicating relatively narrow spectral features consistent with thermally broadened gas at low temperatures. Interestingly, earlier attempts to detect the same transitions in September 2025 had failed, suggesting that the molecular activity of 3I/Atlas increased significantly as it approached and passed its solar conjunction. The observation occurred a few days after 3I/Atlas's solar conjunction, which took place on October 21, 2025. At conjunction, the object's apparent position was nearly aligned with the Sun from Earth's perspective, making direct observations extremely difficult. However, once the angular separation increased slightly, MeerKAT could observe it safely. At that point, the object was moving almost perpendicular to the telescope's line of sight. The reported Doppler velocity of about -15, 6 kilometers per second arises not from the object's full space velocity, which was around 98 kilometers per second relative to Earth, but from the projection of this velocity along the telescope's line of sight. Since the angle between the object's motion and the line of sight was approximately 9.2 degrees, the observed radial component of the motion corresponds well to the measured Doppler shift. 98 times sin 9.2 degrees is almost equal to 15.7 kilometers per second. This perfect consistency strengthens confidence in the interpretation of the signal as genuine absorption by gas associated with 3I/Atlas, rather than an unrelated interstellar cloud. The spectral line widths provide valuable information about the physical state of the gas. The thermal broadening of molecular lines results from the random motion of particles due to their temperature. For a gas composed of OH molecules with molecular mass 17 atomic mass units at a temperature of around 230 K, the expected thermal broadening corresponds to an FWHM of roughly 0.8 kilometers per second, almost identical to the observed values. This agreement implies that the line broadening arises predominantly from thermal motion rather than turbulence or bulk outflow. The estimated temperature of 230 K minus 43 degrees Celsius can be derived from the balance between solar heating and thermal radiation. Given that 3I/Atlas was at a heliocentric distance of 1.38 astronomical units AU at the time of observation, its surface received solar flux weaker by a factor of 1/1.38 superscript 2 compared to Earth. Because the emitted radiation scales with temperature to the fourth power T, the equilibrium temperature scales approximately as 1/√138, leading to the deduced 230 K value. This modest temperature supports the idea that water and other volatiles could sublimate slowly, releasing OH into the surrounding coma. The presence of OH absorption implies that 3I/Atlas retains volatile compounds typical of comets, despite its interstellar origin. This finding strengthens the hypothesis that interstellar objects are not exclusively rocky fragments, but can also include icy bodies similar to comets from our own solar system. The detection further suggests that chemical processes such as water photodissociation, known from solar system comets, also occur around interstellar visitors when they approach the Sun. Comparing 3I/Atlas to previous interstellar objects helps contextualize its significance. 1I/Oumuamua exhibited no detectable gas or dust emission, behaving more like an asteroid or a rocky fragment, while 2I/Borisov displayed a classic cometary coma and tail. The new detection from 3I/Atlas suggests that it falls between these two extremes. It is active enough to produce measurable OH gas, but not bright enough to display strong optical emission. This diversity among interstellar objects hints at varied formation environments and histories across planetary systems in our galaxy. One of the more intriguing coincidences noted by astronomers is the similarity between the arrival direction of 3I/Atlas and that of the famous WOW signal detected in 1977 by the Big Ear Radio Telescope in Ohio. The WOW signal was a powerful, narrowband radio burst at 1,204,556 GHz, close to the hydrogen line frequency, and remains one of the most enigmatic events in SETI history. In 2025, astrophysicist Avi Loeb pointed out that 3I/Atlas's trajectory passed within 9 degrees of the WOW signal's direction. This coincidence, though not evidence of any connection, motivated radio astronomers to monitor 3I/Atlas for potential emissions at similar frequencies. Responding to these calls, radio observatories worldwide, including MeerKAT, began tracking 3I/Atlas. Although no artificial or narrowband radio emission has been detected so far, the discovery of natural OH absorption demonstrates that careful radio monitoring of interstellar visitors can indeed yield valuable scientific results, even if no extraterrestrial signal is found. The story of 3I/Atlas does not end with the October 2025 detection. According to orbital predictions, the object will pass within 53 million kilometers, 0.35 Australian dollars, of Jupiter on March 16, 2026. This close approach presents a unique opportunity for further radio observations. The Juno spacecraft, currently orbiting Jupiter, is equipped with a sensitive dipole antenna capable of detecting radio emissions across a wide frequency range, from 50 Hz to 40 MHz. During the flyby, Juno will search for any low-frequency radio signals originating from the vicinity of 3I/Atlas. If Juno detects such emissions, they could provide clues about interactions between the object and Jupiter's powerful magnetosphere. charged particles and plasma interactions could generate non-thermal radio waves, similar to those observed in solar system comets passing through magnetic environments. Even if no signals are detected, these observations will set valuable upper limits on the radioactivity of interstellar objects. The detection by MeerKAT is significant for several reasons. It marks the first time any radio signal, whether in emission or absorption, has been directly linked to 3I/Atlas. It also demonstrates how changing geometry and increased solar heating can activate volatile release from such objects. The observed Doppler velocities and line widths match expectations from orbital dynamics and thermal physics, confirming the robustness of the interpretation. Observing a faint absorption signal against a strong solar background highlights MeerKAT's exceptional sensitivity and calibration accuracy. Moreover, the event encourages continued monitoring of interstellar objects for both natural and potentially artificial radio signals, bridging planetary science and SETI. The detection of OH molecules in 3I/Atlas provides one more piece of the puzzle in understanding the chemical diversity of planetary systems beyond our own. Each interstellar object that enters our solar system carries with it the molecular fingerprint of its birthplace, the chemistry, radiation environment, and physical processes of another star's debris disk. Studying these materials allows scientists to compare extraterrestrial ices and rocks directly, without leaving our solar system. In the coming decade, next-generation facilities like the Square Kilometer Array, the Vera Rubin Observatory, and JWST will likely detect and analyze many more interstellar bodies. MeerKAT's success with 3I/Atlas demonstrates the feasibility and value of combining radio spectroscopy with optical and infrared tracking. The radio absorption of hydroxyl radicals detected by MeerKAT in the interstellar object 3I/Atlas is a remarkable milestone in observational astrophysics. It links the microscopic world of molecular transitions with the grand-scale motion of a celestial visitor traveling nearly 100 kilometers per second through the solar system. The precision with which the observed velocities, temperatures, and line widths match theoretical expectations testifies to the power of modern radio telescopes. Beyond the immediate data, this discovery reminds us that interstellar visitors are not silent. They carry whispers of chemistry and physics from distant worlds, and with instruments like MeerKAT, humanity is now able to listen.